Imagine a robot working seamlessly, not in a perfect factory, but in a messy, unpredictable world. How does it handle unexpected changes, like a suddenly slippery floor or a tool that is heavier than expected? Adaptive control is absolutely critical for robot autonomy because it allows robots to continuously learn and adjust their behavior in real time, even when facing unknown or changing conditions in their environment or within their own systems. This ensures they can operate reliably, safely, and effectively without constant human intervention. Traditional robot controllers relying on a precise mathematical model of the robot and its environment. This works well in highly structured, predictable settings like assembly lines, where every variable is known and constant. However, the real world is far from constant. Robots encounter uncertainties such as varying loads, friction changes, or even degradation of their own components like motors and gears over time. Without adaptive control, a robot using a fixed model would struggle immensely. Its performance would degrade, it might become unstable, or even fail completely when conditions deviate from its pre-programmed expectations. Adaptive control systems tackle this by actively estimating these unknown parameters and then dynamically modifying their own control laws to compensate. They constantly monitor the robot's performance, compare it against desired behavior, and make adjustments to maintain stability and accuracy. This feedback loop is the core mechanism that allows for robust operation despite inherent uncertainties and disturbances. So, how does this translate into practical capabilities for autonomous robots? Consider a mobile robot navigating uneven outdoor terrain. Adaptive control enables it to automatically adjust its gait or wheel torque to maintain balance and progress across mud, gravel, or inclines, rather than getting stuck or tipping over. For a robotic arm tasked with manipulating objects, adaptive control allows it to automatically compensate for variations in an object's weight, shape, or even its center of mass, leading to a much more dexterous and capable manipulator. This means robots can effectively handle tasks where every detail cannot be precisely modeled beforehand, greatly expanding their utility beyond constrained environments. One fascinating approach within adaptive control is called Model Reference Adaptive Control, or MRAC. In MRAC, the robot's actual performance is compared to a desired performance trajectory, generated by a reference model. The adaptive controller then generates a control signal to minimize the error between the robot's actual output and the reference model's output, essentially guiding the robot to follow the ideal behavior. This sophisticated technique allows for robust performance even when significant uncertainties about the robot's dynamics or environment exist. It enables robots to operate consistently and efficiently over extended periods without needing frequent recalibration or manual tuning. Ultimately, adaptive control is the key ingredient that frees robots from the limitations of fixed, pre-programmed behaviors. By continuously learning and adapting to dynamic situations, it transforms robots from rigid machines into truly autonomous agents capable of performing complex tasks in the messy, unpredictable world we inhabit. This capability is not just an enhancement, but a fundamental requirement for the next generation of intelligent, self-reliant robotic systems.
If you love robotics, like, subscribe, and keep building with us.